Hey kids, welcome to 12.2. This is the warm-up that I will be starting with on our live session on Friday to see if maybe you've been able to do either one of these. All right, and so quickly some notes. Most of you, I know all this, so if you need to speed through this part, it's fine. Just make sure of the notation that you have. Right? You know what a vector is, initial point, terminal point, right? Usually written with the initial point, terminal point, or and a little arrow above it, or with a, a letter, sometimes bold, sometimes italic, whatever. Just kind of, read in context, right? Hopefully you remember how to name a vector, that you are just going from terminal to initial. In 2D or in 3D, same thing. So if I ask you to find this vector, vector AB, and let's say I want to call it V, right? Four minus four, two minus zero, and one minus negative three, right? Magnitude, think absolute value, because the absolute value connection is that it is a distance, it is positive, magnitude is positive. Also, magnitude is a number, right? It is not a vector, it is a number. Right? Whether you're in 2D or 3D. So if I ask you to find the magnitude of this vector, right? 25 plus 9 plus 4. Hopefully I've done my mental math right, and that is the square root of 38. Vector operations, adding, subtracting, multiplying by a scalar, right? So a plus b, 7, negative 1, negative 7, right? Just adding like components. Adding geometrically two vectors, right? Kind of think tip to tail. So I would kind of think of taking this vector, if this is vector A and this is vector B, I would think of taking this tip, putting it on this tail, right? And that is the resultant. Three times A is just multiplying each one of these by 3, yes? Like kind of taking a vector and dilating it almost, right? And in your text is a complete list of the properties. Unit vectors. A unit vector is a vector whose length is 1. Here are some special unit vectors, and hopefully you can see that their length is 1, right? If you did the magnitude of I, j, or k. So when you think of I, j, and k, right? I is the vector here that terminates at 1, has a terminal point. Right, those are special unit vectors. And any vector that we have may be expressed as a linear combination. So what does it mean to be a linear combination? It means you're adding, right? Adding, addition of the opposite is subtraction, right? So if I take this vector 3, 6, negative 2, which you can think about as, right, 3 vector going out 3 units in the I direction, right, or in the X direction, 6 units in the Y direction, and down negative 2, oh dear, down negative 2, down through the floor where that point is. I can write this vector as a combination of 3 times the vector I, right? So 3 times 1, 0, 0 plus 6 times, right? 6 times this vector, right? And if you think about geometrically adding, right? 6 times, and then scalar multiply the j, right? So that's 3i plus 6j minus 2k. So sometimes I just call this the IJK format of a vector. And you need to be comfortable writing vectors, or at least recognize them in both forms. So if I ask you to find 2a plus 3b, and I've given you I, J, and K format, you just need to be able to read that, but you don't have to give it back to me in IJK form, right? I can just think of this as 3, 6, negative 2, 5, negative 1, and 4. Multiply a by, right? Multiply this by 2, so 2a would be 6, 12, and negative 4. And I'm going to add just b, 5, negative 1, and 4. And when I add those together, I get 11, 11, and 0, right? If I was going to write this in IJ form, we don't write 0j, right? All right, if we want a unit vector having the same direction as v, and hopefully this makes sense, that if you have, right, some vector and you find its, right, find the length of it, if you take the same vector and divide by its length, right, you're going to get a unit vector 1. But I want the same direction here. So what do I need to do? I need to find the magnitude of v. 1 plus 4 plus 4, which equals 3. And now take woot woot, check, is the magnitude of this vector 1? I don't need the negative, right, because I'm squaring. One plus 4, common denominator of 3 squared. Yes. Woot woot. Unit vectors often come into play when we start doing a lot of what you might remember from BC calculus, kind of sort of like slope fields, right? Think about how we always drew those little tangent lines to be little short, right? Little short representations of tangent lines, right? If we're trying to draw some kind of force field where we're representing the true length of every vector, and maybe we have large vectors, short vectors, or whatever, it becomes too messy. Whereas if we can maybe unitize every vector, it becomes a more visually pleasing picture, if you will. All right, that last thing that I did kind of where I verified, I might actually, the question might actually ask you to verify. Show that this vector is a unit vector, right? So that if I'm showing this question, just make sure you know vocabulary, right? And you're just doing the square root of each one of these things, right? Squared. Kind of cheating there. And hopefully you can see that's 9 times 2, 16 times 2, and 25 plus 2 times 2, all over the common denominator of 10 squared, which is 100. And yes, you get the square root of 100 over 100, which is the square root of 1, which is 1. Woot, woot. All right, so a quick application. Please don't stress about this problem. It is not critical to multivariable calculus. It is just showing you an application of vectors, and some of you that have taken physics or are in physics will recognize what we're doing here. But please don't stress about like, oh my God, I don't understand what just happened, and is this going to be on some kind of test? Blah blah blah. No, just try to pick it apart and follow what's going on with the representation of and how we use vectors to represent something that's going on in our space, in our world space. So this is just two-dimensional problem. If I've got two wires, right, and I have a 100-pound weight, find the forces, right? And the forces are represented there by T1 and T2, right? And I'm going to do that with vectors, and I also want the magnitude. So here's how I'm going to manipulate this problem. I'm going to take those angles, right, of 50 and 32, and I'm going to create a drawing where I've got another parallel line here, and I'm going to just use alternate interior angles, right? Something, one of the few things I need from geometry, and create some triangles right here. And some special triangles, right? They're going to be, haha, get it, right triangles. And I'm just going to use some triangle trig here. So check out what I've done there. Notice the green vectors that I've drawn. Look at the vector addition happening. So the first thing I'm going to do is express what I'm asked for, T1 and T2. I'm going to break them up into their horizontal and vertical components. So notice that I've got the I and the J here, right? Horizontal and vertical. So take a moment and see if you can figure out what I've done here. Right? Do you see the triangle trig that's happening there? Right? This is, what have I found right here? The horizontal component. Right? That is a horizontal component that I'm going to call an I. How do I get the length of that? Right? Well, the length of this, if I call that instead of an I, what if I just was in triangle trig and called that an X, right? Isn't the cosine of 50 degrees, cosine of 50 degrees is equal to X over the magnitude, right? Or the length of that T1. And I just solved that for X. Here's X. Where'd the negative come from? Yeah, because I'm going left, yes? So do the same thing with Y. Can you see what happened with Y there? How do I find Y? Well, the sine of 50 right? The side of that triangle, Y, is equal to the length of this red vector times sine of 50, and that gives me Y. So this resultant vector, T1, is a result of adding its horizontal component and its vertical component, and I call that the I and the J. And of course, I don't have to. I could have used right? I could have done the same thing. I could have written it in component form, right, like that. Left off the I and the J. I did the same thing here with the triangle to the right. So notice right and up, left and up, horizontal and vertical. So what am I going to do with that information? If you add those tensions, right, they counterbalance that weight. So notice how I've represented the weight here with a vector going down. Do you see that right here? Right, this vector, right, the weight pulling down, right, hanging from these two wires that are counterbalancing its weight. So T1 plus T2 has to equal, counterbalance, down, the weight hanging down. The weight hanging down, right, what is that? It is 100, right? This is going down, this is 100 because the weight was 100. Its direction was 100 down. And now think of this, technically it's 0 I plus 100 down, right? Because it's not going right or left any, it's going straight down, is that vector. So I am now adding, right? Think about just substituting into that equation that I just had. This is T1 plus T2 is equal to 100J. Now I'm just going to, and remember, this is actually 0 I plus 100J. So I'm going to equate like terms. Right? If I have an equal sign here, this part has to be equal to this part. The multiplier, the piece multiplying in quotes, J, has to be equal to 100. Now I've like got a system of equations here, yeah? Algebra. I have a system of equations. So I took this equation here and I got T2 by itself. So what did I do? I moved this over here, became positive, and I divided by cosine 32. And I substituted that into here. So now I have T1 sine 50 plus T2 that I got in terms of T1, magnitude of, times sine 32 is equal to 100. When I was actually doing this, I just left it alone like this, but notice that sine 32 over cosine 32, what that actually could be written as. And now I'm just pulling out my calculator and getting that answer, substituting that, and now getting T2 and getting 64.91. Going all the way back to the original, right? Remember, these were the original equations. I was able to get vector T1, vector T2, and I got the magnitude of each. So the magnitudes of the tensions and then what they actually are, right? How to represent them to counterbalance that 100-pound weight. Woohoo! All right, again, you have one homework problem like this. Try to reproduce exactly what I've done and don't stress about this problem. It is not a highly tested component of multivariable. It's just getting you back into the flow of using vectors. We do use vectors a lot, not necessarily for this kind of physics application, but it was a nice one to demonstrate. All right. So when we get together, I will be checking on that warm up as we start, and then we can work on homework problems together. Okay. See you in class. Take care.